As people all know, he is expert in the holographic, and also recently, I think, with his line defect and S-Duality. So he will talk us about this character expansions, line defect, and S-Duality. So let's welcome.
Thank you very much. Let me thank the organizers for the wonderful conference. Today, I will talk about the topics in the context of line defect correlators and their relations to character expansions and to S-duality. The brief outline is as follows. First, I will describe composite operators and countings with the N24 super Yang-Mills example. Then I will describe line defect correlation functions for Wilson and Tabolt lines. For computing the line defect correlation functions, I will describe a character expansion method that can simplify the computation. By the line defect correlation functions, we can explicitly verify S-duality relations. And then I will describe holographic geometry due to the high representation of Wilson lines. Finally, I will discuss physical interpretations and implications. The gauge gravity correspondence is a non-trivial duality between a quantum theory with gravity in high dimensions and a quantum system in lower dimensions. For example, the super Yang-Mills theory in 3+1 dimensions is a cousin of quantum chromodynamics in 3+1 dimensions. And it has a gravity dual, which is string theory in the ADS5. The correspondents have provided methods for computing exact results in strongly coupled gauge theories and quantum systems. For example, Wilson lines are fundamental observables in the gauge theory, and we can also have baryon-like operators in QCD-like theories. And these baryon-like operators in the gravity dual can be described by brane-like states. And they are instrumental in dual QCD-like theories. I will describe composite operators with the N24 super Yang-Mills example. Let's consider N24 super Yang-Mills with SON gauge group. And we can have composite operators built from even numbers of matrix field Zij. We can define the composite operator in this way, and the chi is a symmetric group character. R is a Young diagram. These operators are built from Kronecker contractions and resemble multi-trace products of even powers of Z. And in the context of N24 super Yang-Mills with SO even gauge algebra, we can also consider another type of operator with Levi-Civita tensor. And the P is 0 or positive, and N is even. And the Young diagram R contains an M-box column from the epsilon tensor, and an even subdiagram to its right. And this epsilon tensor corresponds to a puffing factor, which is present when P equals 0. And for higher P, the puffing factor is attached with even powers. So one can classify the operators into two types. The first type is operators with odd number of epsilon tensors. And they reduce to this class of operators. And another type is operator with an even number of epsilon tensors, and they reduce to the operators in the first class. And this second class of operator with epsilon tensor resembles baryon-like operators. And in the QCD, we can construct baryon operators using epsilon tensor and the quark fields. And these are important IR observables for confining gauge theories. And the Baron-like operator is very similar to this operator with the epsilon tensor. Now we can make a counting of the operators. For example, we can first count the first type of operators without epsilon tensor. And the counting function is f1x. X is a fugacity parameter. This is a generating function, and it counts the operator of the first type, and the coefficient of the xp is the number of operators using p fields. And we can count the second type of operators with one epsilon tensor, and the counting function is f2x. And it has a x to the nth factor. This is because the epsilon tensor corresponds to a column. And the column contributes to the x to the nth power. Therefore, the f2x has a x to the nth power factor. So for the SO2n gauge group, the counting function is fx, and it's the sum of the two functions. So it has a factor 1 plus x to the nth power. And this matches with gravity exactly. Here, this x to the nth power is corresponding to a column. And on the gravity side, it's a D brane wrapping RP3. And n is the size of the brane. And this factor, 1 plus xn, xn to correspond to the brane wrapping number 1, and 1 corresponding to the wrapping number 0. And this is the counting function for the operators. And we can also consider angular force over Yang-Mills with SO2m plus 1 gauge algebra. And in this case, the line operators carry electric and magnetic charges in Z2 cross Z2. There are different representations. The fundamental representation has a dimension 2m plus 1, and the spinor representation has a dimension 2 to the m. There's S-Duality, which relates Wilson line for spin 2m plus 1 theory to the Tohov line for USP 2m. For example, the Wilson line in spinor representation for spin 2m plus 1 is mapped to the Tohov line for USP 2m. And we can compute line defect correlation functions precisely. For example, this is a line defect correlation function with the insertion of k Wilson lines. And it counts the number of operators in the presence of insertion of k Wilson lines. And it's an integral, and there are related techniques. For example, one can use a character expansion method to calculate the line defect correlator. And we can also use generalized Monahan-Nagayama rules. And the line defect correlator also involves integration over the maximal torus. The line defect correlator has a fugacity parameter T and Q. One can also have special limits. We can take a T goes to 1 limit. We can also have a combination Q to the 1/4 times T, and make the combination fixed and finite. And these are special simplified limits. For the spin 2m plus 1 gauge theory, we have very interesting spinor Wilson lines. And the 2-point spinor Wilson line correlator can be computed precisely. And it takes this form, and the result holds for any m, including finite m. For example, for SO3, it takes this form, And for SO5, it's a product of 2 factors. And for SO7, it's a product of 3 factors. The product structure reflects underlying representation theory. And for computing the line defect correlation functions, we can use a character expansion method. Here, this is a line defect correlation function with the insertion of k Wilson lines. And it involves integration on the maximal torus. There's a character and also exponential factor. For the exponential factor, we can use the character expansion method to transform the exponential factor to be linear sum by the character expansion method. For example, we expand this exponential function as a linear sum over lambda. Here, lambda is a partition. When we know the lambda, we know a sequence of integers. And f lambda and m lambda are products. Moreover, we have characters, and we can also expand the characters using power sum functions, p mu, and sum over mu. When we use the character expansion method, the exponential form of the line defect correlators with the k insertions can be transformed as the linear sum over lambda with a coefficient a mu lambda r. And these coefficients are due to the expansion of the characters in the power sum function basis. So this transformed the exponential form into linear sum of lambda. And for the SO2n plus 1 gauge theory, we have spinor Wilson lines, which are very interesting. And we use the spinor character. Then we make a power sum expansion of the character. We then use Menachem-Nagayama rules recursively. For a cycle sigma of length, we can write the character in this way. And for example, for cycle, the character is 2. For the USP2N case, with the insertion of k Wilson lines, the formalism is similar. It involves integration over the maximal torus. And there's characters and also exponential factor. It involved the USP2N specific function, where the PM is a power sum basis using the power sum function PM. We can transform the exponential factor by the character expansion method as a linear sum of the lambda. And when we transform this exponential factor, it becomes sum over lambda. Here, lambda is a partition. F lambda and L lambda are USP specific, and they are products. We can express the USP2N characters by the power sum functions, and we obtain the coefficient B mu lambda r. The k-point line defect correlator for USP2N can be expanded using the linear sum of lambda. So this transforms the exponential form into a linear sum over lambda. Thank you. Yes, F lambda is a product, and L lambda is a product. So once we know the lambda, we know a sequence of integers. Then we can calculate F lambda and L lambda as a product. And the Fi and Li is a USP 2n specific functions. Thank you. Yeah, so the L is in terms of the power sum function. Yeah, and the power sum function is used as a basis. Then we expand the exponential factors as a linear sum. Yes, yes. Yeah, it's a USP specific function. Then we can use integral formula. We can integrate the power sum functions and expand it using characters. And this also reflects the Z2 of the USP2M. We can obtain the expansion coefficient B mu lambda R by using the expansion using the lambda. We can transform the exponential form of the line defect correlator into the linear sum over lambda. And here the coefficient B mu lambda R is from the expansion of the characters. And for example, in the expansion of USP2N characters in the power sum basis, we obtain the coefficient B mu lambda R. In this theory, there's S-Duality. For example, the S-Duality relate spin 2m plus 1 theory to USP2m mod Z2. It maps spin-Wilson line to the 't Hooft line with a magnetic charge half and half. And so we have a map from the spin 2m plus 1 theory to the USP2n theory. And the Wilson line in spin representation is due to the 't Hooft line in the USP2m. And the electric charge in the SP2n plus 1 theory is mapped to the 't Hooft line with a magnetic charge half and half. For example, for spin 7, it's due to USB 6. And the 't Hooft line has magnetic charge half. We can also have the half EPS indices, which match exactly under the S-Duality. For example, the 2-point Wilson line defect correlators in a spinor representation, it has a closed form expression. And we can calculate also the 't Hooft line 2-point correlator with a closed form expression. And these two closed forms are the same. The product formula has a deep mathematical structure. It's related to partitions into distinct parts in the generating function. And it encodes the BPS states counting in both S-dual theories. And this relation demonstrates the S-duality because the line defect correlation functions match precisely. And the Wilson line and 't Hooft line under the S transformation get mapped. Oh, sure. Yes. For Fugacity, one can have for Fugacity T and Q. then it's for T and Q, one can obtain the line defect correlator, which counts the 1/8 BPS states in the presence of K insertions of the line defects. Then one can take limits to obtain unflavored limit or half BPS limits. And both one-way BPS case and the half BPS case has a closed form expressions. So in the half BPS case, we can explicitly see the closed form expression for the 2-point function of the Wilson line in spinor representation, and the 2-point function for the Tohov line are the same. So this verifies the S-duality relation. Yes. Thank you. Yes. Yes, yeah, we can use a matrix integral, and finally we simplify the expression. And for example, in the half BPS case, we obtain the precise form, and the two sides are the same. Thank you. And for high representation of Wilson lines, they are due to gravity geometries, and they take the general form of ADS2 cross S2 cross S4 fibered over a Riemann surface sigma. And so for the SO and SP cases, we perform a Z2 quotient. Before the quotient, the base space is the Riemann surface. And there's fiber ADS2, and the fiber S2 and S4 has a degeneration loci on the Riemann surface. After the Z2 quotient, in the 10-dimensional perspective, there are fixed point. And at the fixed point, the image of S4 becomes RP4. And the S2 is unchanged. There are new topological features due to the RP4 cycles. And in this case, the Wilson line in the spinor representation is due to defibering on ADS2 cross RP4. There are R3 form flux in the gravity dual. For 3 cycles, C3 supporting the defibrating charge, the integration of the F3 over the 3 cycle is quantized. There are also R5 form flux. For 5 cycles C5 supporting the D3 brane charge, the integration of the F5 over the 5 cycle is also quantized. There are effects of the Z2 quotient. The effective flux is doubled in the covering space. And in the gravity geometry, there are topological 3 cycles. They are formed by S2 fibered over segments in the Riemann surface. They support the R3 form flux F3, and they correspond to defibrating charge. These are located near the S4 shrinking loci. There are also topological 5 cycles. They are formed by S4 fibered over segments in sigma, and they support the R5 form flux. These correspond to D3 brane charge, and they are located near the S2 shrinking loci. Then I will discuss physical interpretations and the implications. For the line defect correlators, we can compute the Wilson line defect correlator as well as the Tohov line defect correlator. And the two sides matched precisely. This verifies S-duality relations. For example, for two-point function of a Wilson line in spinor representation in the spin 2m plus 1 theory is equal to the 't Hooft line two-point defect correlator with magnetic charge half, half, half in the USP 2m theory. And for the spinor Wilson line, the holographic interpretation is that it's due to the defibrine wrapping ADS2 cross RP4. And the two-point function of the spinor Wilson line encodes the BPS spectrum. It counts the number of BPS states in the presence of the insertion of two spinor Wilson line. And the line defect correlator has a deep mathematical structures. It has connection to the partitions into distinct parts. And it reflects representation theory of the orthogonal groups. And the product formula suggests deep algebraic structures. There are many related future directions. For example, the line defect correlator is due to gravity spectrum. And for the line defect correlator, one can have a giant Grattan expansions. And the line defect correlator are also related to half indices. They both has a giant Grattan expansions. There are also Fermi gas approach. And there are also high representations and other representations. For the yes, for the question that for more general case, the line defect correlator with frequency T and Q can be both computed in closed form. And we can use the character expansion method to transform the exponential form into the linear sum of the lambda. So this simplifies the line defect correlator. Are there other questions? Yeah. This refers to in the gravity dual, the Wilson line in spinor representation is due to the defibrine on ADS2 cross RP4. And for high representations, for high representations, for large Young diagram, the gravity dual geometry has a various 3 cycles and 5 cycles. And they also have a quotient where the new RP4 cycles occurs. Thank you for the question.
Okay, so I think that's success. So for the question session, I would say, because I think you are computing this Wilson lines insertion in the 48 floor. theory of the algebra SO to n plus one. And so is this technical also for other, for example, for the E-type, you have E6, E7.
Yes. Yeah, as well as SO2M. Yeah.
Yeah, for SO2, yeah. So we know Wilson. Oh,
Yes. Right.
same.
Yes.
So the character expansion is so small characters because they have some modular properties because it's on they should transform on this S transformation.
Yeah. Right. For SO2M, the S2, it's a SO2M is a self S2, and the center is Z4. The method is similar. Thank you.
Thank you for the talk. I was wondering whether you can repeat the same thing for the ABJM theory.
Oh, yes. Thank you. Yes.
Comment on that.
In that case, the Wilson line is also similar. One can use a similar method.
You're perhaps interested in large N limit, right?
Yeah, right.
Do we know the structure of the character for very large N? For small N, I can imagine how you compute it, but for large N, is it clear? How does it begin?
Yes. For large N, we can have characters of this form, and for finite N and large N, both we can compute the characters, and also for the products of characters, we can also expand using character expansions. Because here lambda is a general partition, and so for arbitrary products, we can use the character expansion method for any n.
Thank you for your nice talk. I have two questions. First, what's the physical meaning of the coefficient A? Coefficient A.
Yeah, I see. So because the line defect correlator is an exponential form, we can transform the exponential form into a linear sum to simplify the exponential form. And this will then we can make the expansion of also the character, because it involves k insertions of Wilson line. There's a k factors of the characters. For this product, we can expand using the power sum function p mu. P mu is a power sum function, and the a mu lambda r is a coefficient in this expansion. And then using this expansion with the a mu lambda r coefficient, we can simplify the line defect correlator using the expansion of lambda. Thank you.
And can you elaborate on how your result for n equal 4 SYM might be adopted to more realistic QCD-like series with different matter content?
Yes. Right. Because the Wilson line is a important observable also for the confining gauge theories. Yes. For 40 angle 4 and 40 angle 2, we can use the similar method. And for 40 angle 2 theories, it's a more resemble realistic QCD like theories. And also in this approach, we can not only consider the Wilson line, we can also consider baryon like operators constructed by epsilon tensors. And these baryon like operators also occurs in 4D angle 4 and 4D angle 2 gauge theories resemble QCD like theories. Thank you.
Can I ask? So in your talk, you focus on this SO or SP, some big edge field. How much is understood for UN?
UN is also of the similar formalism, and it's here the SOSP and the UN cases are all very similar.
For example, for the supermagnetics or UN case theory, so you're considering the Wilson line defect index, which is more complicated stuff than supermagnetics. But even for the supermagnetics case, I think no one knows the closed form expression. Your formula looks very simple, but if you consider the supermagnetics with all fugacity turned on, so per counting very less supersymmetric states, then if we are considering shear index, we know. For generic, most generic cases.
I see.
So yeah, that's also my question. So yeah, I think we are also doing some parameter restriction. So not completely generic with some index, but some specialization. Otherwise, I think it's impossible to write down very simple formula, or the calculation is also very complicated. So.
So are there any other questions?
Okay, so thank you for your talk, Professor Ling. I have some rather fundamental questions. Would you please go back to the slide of Wilson line geometry? So it says that after the operation of Z2 quotient, we'll have some new topological features. Can you explain more explicitly what kind of new topological features, and are they related to the fixed points mentioned before? And are these fixed points related to the generation points of the boundary from the surface before quotient? Thank you.
I see. For the Z2 quotient case, there's a Z2 action on the Riemann surface. And from the 10-dimensional point of view, there are fixed point. And this fixed point is on the boundary of this Riemann surface. For example, if on the boundary of the Riemann surface in the S4 shrinking segment, if the fixed point is at the S4 shrinking segment, then at that fixed point, the image of S4 become S4 mod Z2. Because in the covering space, in the 1 to 2 map in the covering space, the RP4 become S4. And this fixed point is from the point of view of 10 dimensions. And so when the fixed point is at the S4 shrinking segment, at the boundary of the Riemann surface, at the fixed point, the S4, the image of S4 becomes RP4. Then there's also ADS2 fibration. So they together form ADS2 cross RP4. In the Z2 quotient, there are new RP4 cycles.
Yeah. So in the ADS CFT dictionary, usually the expectation value of Wilson loop is related to some kind of minimum surface in the block. So I'm wondering if there's some correspondence you can see here.
I see. Yes. Here, if we compute a minimal surface corresponding to Wilson line, it will also show similar features. Because for example, in the paper, one can use a matrix model approach and matches with the gravity computation exactly. So here, one can possibly also use a similar method. Thank you. And also, there are also Fermi gas approach. It would also be interesting to connect to the Fermi gas approach for the BCD type gauge groups. Thank you.
Thank you.
So are there any more questions?
Thank you for your talk. Your systematic approach using gene graviton expansion seems to give exact results to finite n, which is quite remarkable. So I'm wondering, how does the computational efficiency of your method compare to traditional techniques like localization or numerical bootstrap?
Oh, I see. You mean numerical bootstrap and what is the other method? Localization. I see. Right. Because we can possibly connect with numerical bootstrap method, and here we can use analytical method, and it's very efficient due to the character expansion method and due to combinatorial method. So it'd be very interesting if one can also use bootstrap and the ingredients to make a connection and to also have a cross check between different approaches. Here it's analytical, so it's highly efficient for analytical computations.
And the other question is the exact line defect correlators provide an all orders handle on certain BPS observables, which opens the door to investigating resurgence and non-perturbative effects in this context. So I'm also wondering is whether the series expansions or Q series for these defect indices exhibit a form of resurgent transseries structure.
I see. Yeah, it will be very interesting if we can connect with the resurgence method and other non-perturbative method. So here, because the S-Duality is a very useful non-perturbative method, it maps small G string to large G string. And here, it would be nice if we can connect with the resurgence, because in the dual gauge side, we map the GL mu square to 1/GL mu square. So for a strongly coupled gauge theory with big GL mu square, we can map to a weakly coupled GL mu square. By 1/GL mu square. So it would be very nice if we can also connect this approach, this highly efficient analytical approach, to also resurgence, to also non-perturbative effects and instanton effects. This is a very interesting future direction. Thank you.
Thank you for your answer.
Thank you.
Because can you go to the Outlook page for the Fermi gas approach? Because I don't know what is a Fermi gas approach. Can you give me a rough picture of this and how to connect with your result?
Yes, there's a Fermi gas approach for BCD type by Professor Mingxu Huang and collaborator Du and Wang Xin. They can obtain closed form expressions for the BCD type. It's a very interesting future direction. Yes, I'm also looking at the Fermi gas approach for this direction. Thank you.
So if there are no more questions, so let's thank the speaker again.